We're going to shift gears and go back to acceleration now from these velocity versus time graphs that we've been working on for the last couple of days. Specifically, we're going to talk about acceleration because of gravity. And what I want to tell you is that all objects under the influence of gravity, if we neglect air resistance, I'm going to put that little note in there, in the absence of air resistance, accelerate at 9.81 meters per second squared. The demonstration we just did, we crumpled up a piece of paper and we dropped a set of keys, and they hit the ground at the same time because both of those objects, piece of paper, keys, accelerated at negative 9.81 meters per second squared. Now, if we had the piece of paper not balled up, then it would have accelerated at a much slower rate, right? Because there would have been air resistance. But if we crumple it up, then still air resistance, but the air resistance is so small that the acceleration of both of those objects, paper and keys, is going to be pretty close to 9.81 meters per second squared. Why do you think we make it negative, by the way? I don't know if in Science 10 you guys would have talked about that or not, but yeah, it's accelerating downward. It's speeding up in the negative direction, right? Downward is negative, and it's speeding up in the downward or negative direction. Oh, but wait. When we throw an object up into the air, when it's rising up into the air, it also accelerates at negative 9.81. How can you say that something speeding up is negative 9.81, but something slowing down is also negative 9.81? Explain that one for me, huh? Yeah. What causes this acceleration? And I said at the beginning of this unit, we weren't going to talk about what causes the movement. Okay, I lied. We're going to talk ever so briefly about it today, and then we'll spend a lot more time on it in our next unit. But what causes, in both cases, the keys or the piece of paper to accelerate? Whether I drop them from a certain height or whether I throw it up into the air, it's always gravity pulling down, right? If it's a downward force, it's a downward acceleration. Even when it's moving upwards, it's a downward acceleration. Why? Because it's slowing down in the positive direction. So you got an acceleration you got something that's speeding up in the negative direction or slowing down in the positive direction. That's a negative acceleration any way you look at it. So in general, we say that acceleration is negative when an object slows down in the positive direction or speeds up in the negative direction. Now, 9.81 doesn't sound that high, but it actually is. That's a pretty high acceleration, actually. You got to figure that when you guys go on your field trip in a couple months, you're going to make a virtually straight down drop on the Mindbender roller coaster from a height of about 50 meters to a height of 0. You're going to fall 50 meters. 50 meters, half a football field length. You're going to fall that far in about 3 seconds. You're speeding up really, really quickly. And you're going to feel your stomach going up through your throat. That's how quickly you accelerate. How many of you guys have ever been on the top of, like on the observation deck of, anybody ever been to New York and been to the Empire State Building? Yeah? I was actually in New York in August of 2000, and was lucky enough to be able to stand on the top of the World Trade Center, looking out over New York on the top of the World Trade Center a year before it came down, and signs everywhere on the top of the World Trade Center and on the observation deck of the Empire State Building that basically say, listen, if you throw anything off, like some people may like to throw a quarter off and see it accelerate downward for 110 stories. If you throw anything off, basically, you're going to go to jail. Why? Yeah, seriously. Like a building that is 110 stories high, which the World Trade Center was 110 stories high, each story is about 3 meters. You're talking over 300 meters that this thing is going to fall. Okay, that quarter is going to be moving at an unbelievable speed when it hits the ground. It could cause some serious damage to a person if it actually hits somebody. Now, it's not going to be, there's kind of a myth that if you drop a quarter from that height that it's going to embed itself in concrete, like, you know, a foot into concrete. That's not true. How come? What actually happens to that quarter long before it actually reaches the ground? You guys ever heard a term called terminal velocity? It actually reaches a terminal velocity, which means that it doesn't actually accelerate. It just goes down at a constant velocity. And that's because air resistance becomes so big on that quarter, so high upwards because it's going so fast that it actually doesn't speed up anymore. But in order to reach that terminal velocity, it's still got to be going really fast. And that's why you're not allowed to throw things off of there. It's not going as fast as you might think, but it's still going really fast. All right. So objects in the absence of air resistance, which will ignore air resistance and all the problems that we do, objects will fall at 9.81 or negative 9.81, and objects will rise, slow down as they're rising at a rate of negative 9.81 as well. Now, solving these problems becomes a matter of doing whatever you did for all those other acceleration problems, except that now you've got a given automatically built in. That given is A is equal to negative 9.81 meters per second squared. All of these problems will be group B problems because they all involve acceleration. You're allowed to use those 5 acceleration equations that we learned, but make sure that you make A negative 9.81 if it's rising or falling under the influence of just gravity. If there's some other force, okay, all bets are off. Okay, but if it's just gravity, then A will always be negative 9.81. All right, let's take a look at a question on page 57. It says, while cliff diving in Mexico, a diver throws a smooth, round rock straight down with an initial speed of 4 meters per second. The rock takes 22.5 seconds to land in the water. How high is the cliff? A few years ago, my brother-in-law and sister-in-law and their kids have a place at a lake in BC called Maple Lake. Anybody know where Maple Lake is? No? It's coast of Vernon, BC. So they have this beautiful lake kind of way off the road, so fairly quiet and pretty a big lake. So we go out there one summer with my wife and my kids, and we go boating and water skiing and tubing, and then we come to this area where my nephew, who was I think he was maybe 16 or 17 at the time, liked to go cliff jumping off of this cliff. Anyways, he had boat up here, and then to the edge of the cliff that went straight into the water. Now, the good news is here, the cliff, the water, you could tell by the instrument they had, this fish finder instrument that they had on the boat, that the water at the edge there, this lake is unbelievably deep. It's something like 300 meters deep in its deepest point. 300 meters, 3 football fields deep in its deepest point. But the water, even at the edge right here of this cliff, was 100 meters deep. Like right at the edge. The cliff just kept going straight down, straight down, straight down. So if you jump off this cliff, you don't need to worry about hitting the bottom, okay, because you're not going 100 meters deep into that water when you jump off this cliff. And I remember the one day, we're coming up in the boat, and here's the area you jump off of this cliff, and I'm going up into this boat, and I'm thinking, that doesn't look that high. I think I can do that. I think I can jump off this cliff. So then we get up here, and then there's this little path. It's not actually all that hard to get up. A little bit of scrambling, but it's not all that hard to get up there. So we get up there, and then I look out, and I'm like, or I look down, thinking, I don't think I can do this. Like I don't think I can jump off this. It looks so high. And then my nephew who was 16 or 17 at the time says, well, just so you know, there's no way down. The only way down is to jump. So we climb up the cliff, but you realize when you're up there, it's like there's no way you can climb down that cliff the same way. So I stood up there for probably about 5 or 10 minutes trying to get up the courage to jump. Eventually I jumped. And then of course, once you do it once, then you can do it 1,000 times, right? It's just the first time. But I remember my nephew saying, like, I wonder how high this is. Like, I wonder how high this cliff is. So after we had jumped a couple times, said, well, let's measure it. We don't have a tape measure with this, but all we did is take a rock off the side of the cliff and drop it. And if we can time how long it takes the rock to fall and hit the water, we know the acceleration is negative 9.81, then we can calculate the displacement, right? And that's what we're doing in this question, except that when I did this a few years ago, I didn't throw it downward with an initial speed of 4 meters per second. If I want to find the displacement, it's easier to drop it, right? What's the initial velocity when I drop it? 0. So it's easier to do that than it is to throw it at a certain speed, right? But essentially the same thing as these guys in this question here, cliff diving in Mexico. I think we measured the height of it to be, I think it was about, I forget exactly what it was, something like 10 or 15 meters, which doesn't sound all that big, right? 10 or 15 meters, like somewhere between 30 and 50 feet. Like it doesn't sound all that much, but I'm telling you, when you're standing up top of it, it's a high cliff. When you're standing on top of it the first time, at least. Okay, so what do we got here? Is this group A or group B? It's group B because it's the rock is going to be accelerating, right? Throws a rock straight down at 4 meters per second squared. Let's make that negative. We're going to define up as positive and down as negative. Even though everything is downward here, we're still going to go up positive here. My time interval is 2.5 seconds. What else we got? Good. There's nothing other than gravity acting on it once the ball's released or once the rock's released. So we know the acceleration is negative 9.81 meters per second squared. And we're looking for the height of the cliff, right? That's looking for the displacement of the rock, really. I think I'm going to say d is equal to VIT plus 1/2 ET squared. Can I do that? Sure, I can. VI is negative 4. My time interval is 2.5 plus 1/2. And be careful here, negative 9.81 times 2.5 squared. Let's get both of those terms on our calculator. Negative 4 times 2.5 is negative 10 plus, let's say, 0.5 times neg 9.81 times 2.5 squared, negative 30.656. And if we add those together, we get negative 40.656 meters, which if we round it to the correct number of digits, should be 3 digits, negative 40.7 meters. Is that the answer? Yeah, pretty much. What have I just found? The displacement. Have I found the height of the cliff? Technically not. I found the displacement of the rock. What would the height of the cliff be? Positive 40.7 meters, right? Now, if you left it as negative 40.7, am I going to take any marks off for that? No, I'm not. You just understand that technically we haven't found the height, we found the displacement. Good. You guys shouldn't have too much trouble with the questions that we're going to do along with this, right? Because you've done this before. Except that you haven't made a negative 9.81 before, but you made a negative 5. So this isn't any different except the number itself. Okay, let's give these 3 questions a whirl, please. Just a word of caution here, guys. There's 3 questions here. 2 of these questions are straight gravity. One of these questions is not. Okay, one of these questions they throw in there to see if you can distinguish when you're using neg 9.81 and when you're not using negative 9.81. So just be conscious of that as you're reading. Okay? Ask yourself, is it just gravity acting here, or is there something other than gravity acting here so that it accelerates at a rate other than neg 9.81?